So yeah, yesterday we discussed the concepts of laws of motion, and we'll try to solve some problems on each concept. So we'll get a better idea on each. We started with this one. మనం ఈ మొమెంటం అనే ఫార్ములాని, మొమెంటం అనే ఫిజికల్ క్వాంటిటీని న్యూమరికల్ గా రిప్రజెంట్ చేయడానికి ట్రై చేసాం. దట్ ఈస్ momentum of a body is product of its mass and velocity, and this is a vector. అండ్ ఒకసారి దీనిపైన దాని తర్వాత ఇది కూడా చూసాం. ఫోర్స్ ఇస్ ద రేట్ ఆఫ్ చేంజ్ ఆఫ్ మొమెంటం, ఎఫ్ బార్ ఈక్వల్ టు డిపి బార్ బై డిటి, ఆర్ ఎల్స్ ఒకవేళ లాంగర్ టైం ఇంటర్వల్స్ చూస్తే డెల్టా పి బార్ బై డెల్టా టి. ఇది చూసాం. సో దీనిపైన కొన్ని క్వశ్చన్స్ చూద్దాం. ఓకే, సింపుల్ క్యాలిక్యులేషన్స్. గివెన్ ద మ్యాగ్నిట్యూడ్ అండ్ ఒక ఎగ్జాంపుల్ ఇచ్చారు మనకి. ఈ ఎగ్జాంపుల్ కి దీనిపైన ఉన్న ఫోర్స్ ఇంకా డైరెక్షన్ ఆఫ్ ఫోర్స్ ఇంకా మ్యాగ్నిట్యూడ్ ఆఫ్ ఫోర్స్ అడిగారు. ఫస్ట్ది ఒక రెయిన్ డ్రాప్ ఉంది, అది గ్రౌండ్ పైన పడుతుంది, దట్ విత్ కాన్స్టెంట్ స్పీడ్. ఇప్పుడు రెయిన్ డ్రాప్ కిందకి పడుతుంది అంటే దాని వెలాసిటీ డైరెక్షన్ ఏంటి? ఇప్పుడు కిందకే ఉంటుంది. దట్ మీన్స్ డైరెక్షన్ ఈస్ కాన్స్టెంట్. అండ్ దెన్ అతను ఏం మెన్షన్ చేశాడు? కాన్స్టెంట్ స్పీడ్ అని మెన్షన్ చేశాడు, విచ్ మీన్స్ magnitude is also constant. And this means at two different time intervals లో తీసుకుంటే P1 P2 అని, పాయింట్ 1 దగ్గర మొమెంటం ఎంత అవుతుంది? సమ్ m ఇంటూ ఆ పాయింట్ లో సమ్ స్పీడ్ v అనుకుంది. పాయింట్ 2 దగ్గర మళ్ళీ సేమ్ m ఇంటూ v, ఎందుకంటే కాన్స్టెంట్ స్పీడ్ ఇచ్చాడు కాబట్టి. మొమెంటం లో చేంజ్ లేదు. సో మొమెంటం చేంజ్ అవ్వట్లేదు అంటే దానిపైన నెట్ ఎక్స్టర్నల్ ఫోర్స్ 0 అని. యా, సో this case net force equal to 0. A cork of mass 10 grams is floating on water. A cork of mass 10 grams is floating on water. ఇప్పుడు ఒక ఆబ్జెక్ట్ ఫ్లోట్ అవుతుంది అంటే అది ఈక్విలిబ్రియం లో ఉంది. మేము yesterday we discussed about equilibrium. When a body is in equilibrium, the net force acting on the body is always 0. ఇది మనం డిస్కస్ చేసాం నిన్న. వన్స్ ఒకసారి మీరు వెనక్కి చూస్తే మీకు కనిపిస్తుంది. అండ్ ఇప్పుడు ఇదైంది. ఓకే, ఐ థింక్ మీరు ముందుకెళ్తే చిన్న ఎగ్జాంపుల్స్ మీరు చేసుకోగలుగుతారు. సో మనం నెక్స్ట్ క్వశ్చన్ చూద్దాం. 5.2. A pebble of mass 0.05 kg, a pebble of mass 0.05 kg is thrown vertically upwards. Give the direction and magnitude of net force on the, is the screen visible or has it stopped? A pebble of mass 0.05 kg is thrown vertically upwards. Give the direction and magnitude of net force on the pebble during its upward motion, during its downwards motion, at the highest point where it is at momentarily rest. An object is thrown upwards. Then mass 0.05 kg ఇచ్చారు. If this is thrown upwards, and we know that the gravity always exists, 10 meter per second square. Let's assume. So ఇది పైకి వెళ్తున్నప్పుడు దీనిపైన యాక్ట్ చేసే ఓన్లీ ఇది ఎవరితోనూ ఇప్పుడు మనం చెక్ చేద్దాం ఏ ఫోర్సెస్ యాక్ట్ అవ్వచ్చు. ఇది పైకి వెళ్తుంది. సో అండ్ ఇన్ ద ప్రెసెన్స్ ఆఫ్ ఎక్స్టర్నల్ ఫీల్డ్, సో mg అనే వెయిట్ కిందకి యాక్ట్ చేస్తుంది. ఇది ఏదైనా సర్ఫేస్ తో కాంటాక్ట్ లో ఉందా? లేదు. సో there will be no normal forces acting on the body. So the net force acting on the body is just mg. And when it is coming down, the same principle again. It is in a field, it is in a gravitational field. So a gravitational force acts on it. But and it's not in contact with any surface. So there's no normal force, so the free body diagram will remain the same. And it was something else. At the highest point, when it is at momentarily rest, this is while going up, this is while coming down, and this is at this topmost point. What happens? Like at this, again, the free body diagram remains same in the three cases. And let's say we project it at an angle 45 degrees. That's what he has given in the last. So again, the only force in this field is the gravitational force acting on it, and there's no contact. So the only force acting on this is mg, which is 0.05 into 10, 0.5 newtons. So okay. Now let's talk about 5.3. What is 5.3? Give the magnitude and direction of net force acting on a star. Okay, so this is a similar question. We could do it. Given the end of a string of length, given one end of a string is connected to a particle of mass m and other to a small peg on a horizontal table, if the particle moves towards the particle moves with the speed v, the net force acting on the particle towards the center. So this is what he's trying to say. There is some bolt or peg kind of thing, and to this there is an object of mass m connected, and this is trying to move in a circular motion about. This is trying to move in a circle about this. So, and there will be a tension, and it starts to move with a velocity v. And he asked what is the tension on the string. As we discussed yesterday, let's solve it in both the frame of references. Firstly, we'll solve an inertial frame of reference, and secondly, we'll solve it in non-inertial frame. So, in inertial frame, there will be a net acceleration of v square by r towards the center. So, our force equation will be, we know that net force equal to mass into acceleration. We know the acceleration to be v square by r, and let's see the forces acting on the block. This is the block. The only force acting on this is t. So, and acceleration is in the same direction, t. So, t equal to mv square by r. T equal to, and let's solve it in the non-inertial frame of reference. In the non-inertial frame of reference, yesterday I told you that there will be a pseudo force. Why is the pseudo force getting created? Because of the acceleration of the frame. And the pseudo force will always be in the opposite direction of the acceleration of the frame of reference. And we know the acceleration of the frame of reference is v square by r towards the center. So the pseudo force, F pseudo is equal to mv square by r away from the center. Away from the center. So yeah, and in the non-inertial frame of reference, the net acceleration will be always zero, which makes the net to be zero. And the net force acting on the body is T minus F pseudo, which again gives us T equal to mv square by r. And what did he ask us in the question? If the particle moves in a circle, the speed, the net force on the particle is. The net force on the particle is always the tension acting on it. Since there is only one force acting on it, the net force is always. So, okay. And when it comes to the net force calculations, never use non-inertial frames. Never use the forces which we get by solving the equations in non-inertial frame, and never the resultant or the net forces. To this, we always have to use inertial frame of references. In this, the only force acting on it is T. So the net force acting on the ball is T, which is equal to mv square by r. This is 5.3. So this made something clear. India. Let's go to 5.5. What is 5.5? A constant retarding force of 50 newtons is applied on a body of mass 20 kg moving with initially. How long does it take a body to stop? Okay. Okay. Yeah. 5.5. A constant force of 15 newtons is applied on a body of mass 20 kg moving initially with a speed of 15 meters per second. How long does the body take to stop? So yeah, here is our body, and it is moving with some velocity v, and then a retarding force. A retarding force in the sense the force is applied in the opposite direction of the motion of the body, and we are given the velocity to be 15 meters per second, and the opposing force to be 15 newtons, and the mass of the body. The mass of the body is given as 20 kg. So yeah, first we will solve the force equations. The net force acting on the body is 50 newtons in the backward direction. So, and let's say this direction is positive, which makes minus 50 equal to mass into acceleration, since force is the only force, like F is the only force acting on it. 20 into A minus 50, which gives us minus 50 by 20, which is minus 2.5 meter per second square. Okay. And what did he ask? How long will it take for the object to go to rest or to stop? And we know V equal to U plus AT. These are already covered in kinematics. So yeah, for the object to be finally at rest, V should become 0, and U is given as 15 meter per second. Acceleration is plus minus 2.5 into T, which gives us 15 equal to 2.5 into T. Time equal to 15 by 2.5, which is 6 seconds. So it takes 6 seconds for the retarding force to stop the object. This is 5.5. Is similar, yeah. 7, this simple vector equations. And the driver of a three-wheeler sees a child standing. What is the average retarding force on the vehicle? The mass of the driver is okay. Hope you are at the question. The driver of a three-wheeler is moving with a speed of 30, that is moving at 36 kmph. He sees a child and wants to stop the car in 4 seconds, just in time to save the child. What is the average retarding force on the vehicle? He gave the mass of the vehicle as well as the driver. Let's see this. So there's a vehicle and there's a man inside it, like the driver. Let's say his mass is m1 and the vehicle's mass is m2. And he saw a kid on the road and he wants to stop the car before it hits the child. And that he wants to stop the car in 4 seconds. Yeah, okay. And it's moving with a velocity v1. Let's try to solve it generally and then put the values inside. So, consider this as a complete system. So the total mass of the system will be m1 plus m2, and that is moving with a velocity v1. And for the object to go there and stop, the final velocity should become 0. If the final velocity becomes 0, this is the initial momentum. What is the final momentum? 0, since velocity is 0. So the change in momentum is P final minus P initial, which is minus of m1 plus m2 into v1. And this should happen in a time interval of some delta t, which we mentioned. So the net retarding force will be, as you know from the equation, delta p by delta t, which is minus of m1 plus m2 into v1 by the time he has given. This will be the equation. And he gave some values. We'll just try to replace those. Minus of 400 kg of the vehicle, 65 kg of the man, into 65 kg of the man. And the velocity of the car is, he gave it to be 36 kmph. 36 kilometer per hour. And since all the units are in meter, second, and kg, we'll try to convert this to meter per second, which is 36 into 5 by 18, 10 meter per second. So yeah, 10 meter per second. And we need to stop this in 4 seconds. So minus 465 into 10 by 4. Cancel. So 2. Okay, this comes out to be minus 1162.5. Yeah. Yeah. Mm-hmm. So yeah, that's how we do such questions. And now yeah, we'll go for some other question. Like yeah, these type of problems are very common. The problems which the man is inside a lift and all. And then we'll try to see some pendulum questions too. Let's see this example 5.13. 5.13. A man of mass 70 kgs is standing inside a lift. A man of mass 70 kgs is standing inside a lift, which is moving. And then he gave some values for this. So yeah, he's on a weighting scale. Okay. Let's talk. We'll talk about a weight machine. Weight machine. How does a weight machine work? Weight machine doesn't calculate your weight. Instead, it calculates the force you exert on it, which is you are in contact with the weight machine and you're exerting the force on it. So what will it measure? The normal force. Yes, exactly. The normal force. The normal force you exert on it. And it, in turn, from Newton's third law of motion, it exerts its normal force of N over U. So yeah, a weight machine always measures the normal force only. So that is a good point to remember. And now we'll try solving questions. Let's come to this example. A man of mass 70 is in a lift and the lift is moving upwards with a uniform speed. So yeah, case 1, lift is moving upwards with a uniform speed of 5 meter per second. Mass of the man is 70 kgs. And in B case, it is accelerating down with an acceleration of 5 meter per second square. In C case, it is accelerating up with 5 meter per second square. And in the case of D, free fall. So yeah, these are the 4 cases we need to solve. And every time he is in a lift and there's a weight machine below him, it shows the weight. Okay. In the case of uniform velocity, if it is moving upwards with a uniform velocity of 5 meter per second, so the net force on the system is 0. Net force on the system is 0, which means acceleration of the system is 0. So acceleration of the man is 0, acceleration of this is 0. So let's talk about man. What are the forces acting on him? There is a gravitational force acting on him, mg, and there is the contact force, the normal force acting on it. And what are the forces acting on this? The normal force from the man, and there is another normal force from the surface m1, and it too has its own weight. But these are all not, because the spring is on the front surface. For a weight measuring machine, the spring is on the front side, so then only normal exerted from the top matters, and these don't matter. So yeah, and the net acceleration of the man is 0 in case A, which makes us n equal to mg. So reading of the weight machine will be 70 into 10, 700 newtons, or simply 70 kgs. Okay. And the second case, the lift is moving down with an acceleration of 5 meter per second square. So let's consider our free body diagram of the man again. So if it's accelerating down with an acceleration of 5 meter per second square, So m into 5 meter per second square equal to mg minus n, isn't it? Which makes a run to be m of g minus a. Its acceleration is a meter per second square, which is m of 10 minus 5. Uh, so m of 10 minus 5, which is 70 into 5, 350. And the machine is calibrated such that it takes the force and makes it by g to give you the weight reading. The force is the machine is always calibrated in this way. So here we got a force of 350 newtons divided by g value 10. So it will only show a reading of 35 kg. So in a lift accelerating downwards, the reading in the machine is always lesser. Now, in a lift accelerating upwards with an acceleration of 5 meter per second square. So again, seeing the free body diagram, and the net acceleration now is in the upward direction. So it will be n minus mg equal to ma. So the normal force becomes m of g plus a. And the weight reading becomes m of g plus a. I told you it is calibrated using g. So m of 1 plus a by g. And how much did he give it? M of 1 plus 5 by 10. 70 into 3 by 2. 105 kgs. So yeah, when it's accelerating in the upper direction, it gives us 105 kg. D is a very important case. Free fall. Free fall in the sense lift is left free. So let's say a ball is dropped freely. What is the acceleration of the ball? G, right? Free fall. We have considered similar cases in kinematics and all. So the acceleration of the lift will be G, free fall. So consider the man. There is an object force acting on in the upward direction, and the weight acting in the downward direction is mg, and his net acceleration downwards is g. So mass into acceleration equal to mass into g minus m, and we somehow have acceleration equal to g, mg equal to mg minus m, which gives us n as 0. So reading is 0. In free fall, reading of the weight machine is always 0, 0. Okay. This is the special example of lift case, and this is a very good example. You try solving this on your own, so you'll get a better clarity. And we'll do some questions of circular motion too, and some oscillatory motions. Okay, we'll see 5.12. A bob of mass 0.1 kg is hung from the ceiling of a room by a string 2 meters long is set into oscillation. The speed of the bob at its main position is 1 meter per second. What is the trajectory of the bob if the string is cut when object is at the extreme position? Okay. There is this example. There is a pendulum attached. This is the construction of a pendulum, and this is called the main position. And when it's pendulum in the sense, you remember, right? Pendulums of a clock. They swing forth and back like this, and this is called the extreme position. Okay, and there will be some concepts that at the bottommost point you will get to know y and y in simple harmonic motion chapter. At the bottommost point, it will be of maximum velocity. And here the velocity of the object is 0. Here the velocity of the object is maximum. So if you cut this string at this point, because of this, now there's gravity. It will be a projectile motion and then it comes like this. It comes to the ground like this. But here there's no velocity, and you cut the string. So it's just free fall. It falls directly, comes and falls here. So yeah, this is difference when you cut the string at the two different positions in pendulum motion. Okay, mm. Connected blocks. This is a good example. I'm talking about this question. Two bodies are connected by a string, and then force is applied on another block. This is the case he's talking about. Yeah. Its mass is 10 kgs, its mass is 20 kgs, and there is a rope in between. And a horizontal force of 600 newtons is applied on, let's say this is A and this is B. First 600 newtons is applied here. What are the accelerations of the blocks and tensions? This could be asked. So let's say the string is T. Tension is always a pulling force, never a pushing force. So it will always pull the objects. So yeah, and since the objects are connected by a taut string, like a strain string, it is constrained that both the accelerations of the object should be should be the same. So 600 minus T equal to 20 into A, mass. Net force equal to mass into acceleration. T equal to 10 into A. This is for this. This is for this. So from this, if we add these two equations, T gets cancelled out. 600 equal to 30A. This means acceleration equal to 20 meters per second speed. And then tension is equal to 10 into A, which is 200 newtons. We calculate. And yeah, this could be done in a better way. If we, since both the motions are constrained and to be moved in the same way, and the force is applied in this direction, okay. So we can consider the entire mass of the system to be m1 plus m2, and an object moving with an acceleration of a. So 600 newtons equal to m1 plus m2 into acceleration, which gives us the acceleration as 600 by 10 plus 20, which is again 20. So yeah, this could be a better way to solve this problem. But then the tension calculation, since we are applying force on this object, tension is the only reason the second object is moving. So tension will be mass of the other object where the force is not applied into acceleration. So if you split open this equation in two cases, you'll get the answers for both. So yeah, this is a good model of question. And yeah, for practice, you can do this question in the later point of time. And now we'll solve some problems on law of conservation of momentum, which is a very important concept. Law of conservation of momentum. Let's talk about the example given. A nucleus is at rest in laboratory frame of reference, so that if it disintegrates into two smaller nuclei, the products must move in opposite directions, of the children. Let's say this is initially a nuclei sitting at rest in a laboratory, and suddenly, due to some internal explosions, it got broken up. So, and they start to move in opposite directions, obviously. So that should be obvious. If an explosion occurs in between, let's say some explosion occurs here, so all the objects will be moving away from this point, right? Like if a bomb explodes, all the objects will move away from this, like all the dust and stuff. This should be pretty obvious. So yeah, here, what did he ask us? Show that if it disintegrates into smoke, prove that they must move in opposite directions. Okay. Let's consider this case. Let the mass of this half be m1 and this half be m2. This velocity be v2, velocity be v1. Consider this as an entire system. Is there any external force acting on it? No. Internal forces never change the moment of the system. Internal forces never change the momentum of the system. And there is no external force acting on the object which says that the momentum of the system should remain conserved. Momentum of the system should remain conserved. That means P initial equal to P final. What is P initial? Initially, the nuclei is at rest, the parent nuclei. So the initial momentum is 0. And after this, the final momentum from this is, let's consider this direction to be positive. M2V2. And let's suppose we don't know the directions. And we assume them to be in the same direction. V1, not in this direction, but let's consider this M1 to be moving in this direction. So yeah, M2V2 plus M1V1. But then P initial should be equal to P final, which gives us M2V2 plus M1V1 equal to 0. V2 equal to minus M1V1 by M2. So masses are scalars, they can't be negative. So if velocity 1 is positive, velocity 2 should be negative, which implies the velocity should be in opposite directions if an object has been broken. This is a good application of conservation of momentum. And going further, you'll see many applications. Two billiard balls move in opposite directions and collide and rebound with the same speed. What is the impulse imparted? Okay. There will be some very good applications. This is one, gun firing problem. Gun firing problem is a very good example of law of conservation of momentum. Let's consider this. We have a gun and we have this bullet inside. Initially, we didn't fire it. And then after some time, we fired it. So the bullet moves in the forward direction. And because of the firing of the gun, we'll obviously feel that we are pushed back because of it's called recoil. And it gets some recoil velocity, VR. Okay. So again, we can find what is the recoil velocity depending on the velocity of the bullet and mass of the bullet, mass of the gun. Okay. How can we do this? Initially, consider this to be a system. Is there any external force acting on it? No. And if there is no external force, how are they suddenly gaining velocities? You can ask this. This is a valid question actually. Yeah, because of the internal forces, there will be some chemical gunpowder, right? That will be the internal force of the system. If an internal force does some work or does something, and because of this, the velocities are imparting. Yeah, it doesn't change the momentum of the system. It changes the momentum of individual objects, yes, but for the complete system, no. So the initial momentum is 0 because the velocities are 0, and the final momentum is okay. Let's say the velocity here given is velocity with respect to ground. There will be another case. We'll solve it just after this. What if the velocity is given with respect to gun? Okay. Let's say it's with respect to ground. The final momentum will be mass of the positive direction this side, right? Mass of the bullet into velocity of the bullet minus mass of the gun into recoil velocity. So this gives us the recoil velocity of gun as mass of the bullet into velocity by mass of the gun. So yeah, this is just simple. But what if the velocity given is with respect to the gun? What if the velocity given is with respect to the gun? This changes our equations. We need to always apply law of conservation of momentum in an inertial frame of reference or rest frame of reference. The gun here is accelerating, that's for sure. And the velocities we are calculating are just impacted just after the impact kind of things. So yeah. So gun is moving backwards with the VR, and velocity of the bullet with respect to the gun is V. So velocity of bullet with respect to ground will be velocity plus velocity of the gun, which is obvious because VB minus VG. This should be the case. and velocity of the gun is minus vr plus, because it's in the opposite direction, v minus vr. This is the velocity with respect to ground. And now we'll apply the momentum equation again. 0 equal to mass of the gun into velocity of recoil. Sorry. Mass of the bullet into velocity minus velocity of recoil minus mass of the gun into velocity of recoil. And now we get the velocity of recoil as mass of the bullet into velocity by mass of the bullet plus mass of the gun. The answer changed significantly. Yeah, there is significant change in answer. There's a significant change in answer. If you see, there's a significant change. So read the question very carefully, whether they have given the velocity with respect to ground or with respect to gun. Okay. So yeah, this is a very good case, and then there's a huge chance of doing errors in this case. So yeah. Okay. A batsman deflects a ball by an angle of 45 degrees without changing its initial speed. Without changing its initial speed, which is equal to 54 kmph. What is the impulse imparted to the ball? So yeah, there is a bat which is striking a ball, and the ball came and it bent. Let's consider it something like this. The ball deflects by an angle of 45 degrees. The batsman deflects a ball by an angle of 45 degrees. Okay. Okay. Let's say the ball has come like this and it got deflected because it struck the bat. And he told the speed of the object did not change. So let's say it came with u meter per second. It still went back with u meter per second. And its initial direction is this one. And this is the final direction. So how much did it get deflected by? Or else sometimes we'll also say this one to be the angle of deflection. But yeah, but mostly we have to consider this one. This is the theta, the angle of deviation. That is, from the original path, it deviated by an angle theta. Okay? Yeah. So what is the change? What is the force impacted by the force, or the impulse impacted on the impulse in the bat? Okay. So let's talk about this. It is traveling with u meter per second. What is the angle here? If this is theta, this will be 180 minus theta, and this is the bisector. So this will be 90 minus theta by 2, and this is 90 minus theta by 2. If this is 90 minus theta by 2, this will also be 90 minus theta by 2, which makes this to be 90 minus theta by 2. So the horizontal components of this velocities are u sin theta by 2 and u cos theta by 2. This is the initial case before the collision. After the collision, finally, the velocity became like this, which means it became u sin theta by 2 now and u cos theta by 2. So momentum being a vector quantity, all the different axial momentums are calculated differently, and then squared and the resultant is calculated finally. So for that, there is no change of momentum in the vertical direction. So delta py is equal to 0, and in the x direction, the momentum change is u sin theta by 2 minus u sin theta by 2, which is 2u sin theta by 2. And finally, as I told you, delta p is, there are three directions: x direction square plus y direction square plus z direction square. And here we don't have this z and z to be zeros, which gives us delta p equal to px, which is 2u sin theta by 2. So yeah, this makes the equation. So I'm not solving numerically, because if I solve it completely, it would be of no help. You need to practicing the questions. Then only it'll be perfect in all. And okay, 5.23 is another good question. The horse and the cart problem. This is a very famous problem. Explain why a horse cannot pull a cart. So explain why. Okay, the first one. The horse cannot pull a cart and run in empty space. How does this horse pull a cart? Let's talk about this. There is a cart with wheels, and then there is this horse. Let's say this is some horse, and there are ropes tied, whether it will pull it. This is how it works. And while it is trying to horse is trying to run, see the formation of its legs. It tries to be something like this, right? And then imagine how you are running. This is the first, and then it slowly your leg becomes straight, and then again you bend it back. This basically goes like you try to push the ground backward, and the ground will push you forward. The only way this can happen is because of the friction. If there's no friction, the horse can never. If the horse tries to push the floor backward, it just slips and falls. Consider a smooth floor, and you're trying to run on it. What happens? You'll slip and fall, right? The same case. If there is no friction, the horse can never run on a floor. I think no one can run on anything without friction. Friction is the only reason. So because of this friction, it is trying to run, and because of the ropes, there is some tension in this, and this tension is pulling this vehicle. This is how a horse pulling a cart works. And if it is in empty space, let's say vacuum, there's no something called friction in vacuum. There's no concept of friction in vacuum. So if there's no friction, it can't run. So the cart can't be pulled. This is in case of a rough floor. But sometimes we can also consider the normal to be bent. Passengers are thrown forward from the seats when a speeding bus stops suddenly. Okay. What is Newton's first law? Law of inertia. An object in motion tries to continue its state of motion. So there is this bus and there is this guy. The bus is moving with a velocity v meter per second. So from a ground frame of reference, he is also moving with a v meter per second. Bus is also moving with a v meter per second. And suddenly the bus stopped. What is the inertial feeling of the man? He doesn't know the bus stopped. So his inertial nature will be, he tries to continue with v meter per second. So suddenly when the bus stops, you try to get pushed in the forward direction. Like you get to be thrown forward in the forward direction. This is why it happens. Okay. It is easier to pull a lawnmower than to push it. Okay. Lawnmower. This is a very good example. There are many numericals on this. Let's say this is the lawnmower, and you try. First case, you try to pull it with a force. The second case, you try to push it with a force. Which is easier? Firstly, let's talk if the surface is smooth. If the surface is smooth, let's say to pull the object, you just need some non-zero force. So let's say this is theta, and this is theta. F cos theta should be greater than 0. This is the only condition. Here, F cos theta should be greater than 0. This is the only condition. So both the cases are same. The difference comes when there's friction. Let's say there's a coefficient of friction is mu. Here also, let's say the coefficient of friction is mu. Okay. Let's try to draw the free body diagram in this case. There's this normal force acting on the body, a force acting F at an angle theta, and there's the weight of the object. So let's try for equilibrium in the y direction. N plus F sine theta equal to mg, and there's some friction trying to stop this. It's called F cos theta minus F equal to m. These are the equations. Coming to this case, let's try to the free body diagram. is this, that there is a force on the object, normal force, and then mg. This is at an angle theta. So yeah, n equal to mg plus for the equilibrium in x direction, y direction, because the block doesn't either fly or go inside the ground, f sine theta. And for the object to move, f cos theta minus f equal to m. Let's say just to the starting point. So if it just equals to the static friction, it moves. Here also f cos theta just equals to the static friction, it moves. So the force in the case of pull will be mu s n by cos theta, and the normal force here is mg minus f f sine theta by cos theta. Here f cos theta equal to mg plus f sine theta into mu. So it's like you're able to see it, right? F finally equals mu s mg by cos theta plus mu s sine theta. In this case, mu s mg by cos theta minus mu sine theta. The same term is getting divided by something bigger, something smaller, which obviously gives us this. This value is lower, this value is higher. We are trying to apply a lower force. That means pulling is easier. This is the result we get. So this could be used in multiple cases, and this mathematical representations, these will always help you to get a solid answer. So always try to draw the free body diagrams and then try to solve them. And there is this other question, right? What is this? A cricketer moves his hands backwards while holding a catch. Okay. Why is this? You might have seen in every possible cricket match that they always pull the hands back. There is this ball coming, and these are the hands. He tries to pull it back. But why is it? Let's talk about the initial state and final state. Initial state, ball is moving with, let's say, 10 meter per second, and finally it goes to rest, 0 meter per second. So the change in momentum is always fixed. Mass of the ball into 10 meter per second. So let's say 1 kg block, 10 kg meter per second. This is the fixed change in momentum always. So why is he pulling back? We do. This is to reduce the force on his hands. Let's say there is a harsh blow on your hand, it will pain too much. So in order to reduce the pain, we need to reduce the force of impact. To reduce the force of impact, and we know the force to be change in momentum by change in time, and the momentum's value is fixed. So the only variable which is in our hand is the time in which we bring the ball to the rest. Suppose you stop the ball just after catching it. Your time is almost equal to 0, like let's say 0.1 second or 0.2 seconds something. That means your force is 100 newtons here. A 100 newton force acts on your body. Let's say you try to slow it down to 2 seconds, and you slowly pull the ball and then stop it at a farther point than where you catch it. And let's say you took 2 seconds to catch it now. The force on your hand will be just 5 newtons. So what do you think is a rational choice? It's obviously pulling back, right? So yeah. This covers most of the theory and the applications of each concept. Yeah. Yes. So let's do a good question. Something. Okay. Many good questions. Let's do this. A stream of water flowing horizontally with a speed of 15 meter per second gushes out of a tube of cross-sectional area 10.01 meters square and hits a vertical wall nearby. What is the force exerted by this on the wall? Assuming it does not rebound. Okay. Let's say there is this cross-sectional area of water, and this water is coming out, and it then hits a wall and then it flows down, like it goes to rest directly. So yeah, it's coming with what velocity? 15 meter per second and 0.0. Area of cross section is 0.01 meter square, and this is coming out with a 15 meter per second. What is the force exerted on the wall? What is the force on the wall? So let's talk about this water molecules. Everything is coming at 15 meter per second, and then um, it's the and then it's going to rest suddenly. So let dm be the mass of particle. It's moving at 15 meter per second, and then suddenly going to rest. So the delta p here is the change in momentum here is dm into 15 meter per second. Okay, and now let's observe it over 1 second interval. In 1 second, how much amount of water is produced here? 1 second, 0.10 meter per second square, 15 meter per second into 1 second. That means 15 meters. So this 15 meters of length of water comes out in this 1 second. So 15 meters into 0.01 meter square, that is 0.15 meter cube. This much volume of water comes out in 1 second. And this, what is the weight of this? We know the density of water to be 1000 kg per meter cube. This gives us 150 kgs. 150 kgs of water is coming, and then it's striking the wall and going down. So in 1 second, the change of momentum of the whole mass is 150 kg into 15. This is it, right? Into 15. 2250 kg meter per second. This is the change in momentum in 1 second. So what will be the force? Delta P by delta T, which is 2250 kg meter per second per 1 second, which is 22 kg meter per second square. So yeah, which is 2250 newtons. This is the force on the wall. Okay, where did this go? Yeah, okay, this more or less sums it up. And I would like to add a question of my own. Like, there is a very famous concept of block on block. I'll try to discuss a question with you. Let's say there is a block of mass 10 kgs, and then there is a block of mass 5 kg over it, and the surface here has a coefficient of friction, let's say 0.2, and then I try to pull it with a 10 Newton force. Okay, let's say 20 Newton force. What happens? What will be the final state of the system? This is a question. I want the final accelerations of 5 kg block. I want the final acceleration of 10 kg block. And what is the friction force acting between them? This is the question. And I want you to solve this. And before solving this, as I told you, for every mechanics question, any question in mechanics, drawing the free body diagrams is very important. So let's start by drawing the free body diagrams. First, for the 5 kg block, there is a force of 20 newtons acting this side. So obviously there will be a friction acting this side. There will be a normal from the above block, and the weight mg acting on it. And let's talk about this 10 kg block. 10 kg. There is a friction acting forward on this. So where is the reaction of this friction? That will be forward here. That will be of the same magnitude as friction F. And now this is frictionless surface. Let's say mu is 0 here. There can be questions where it has a coefficient of friction too. So yeah, and normal from the surface n1, and there is the upper normal acting on it and its own weight mg. So yeah, this more or less sums it up. Yeah. Now let's try to calculate the accelerations. 25 into acceleration of 5 kg, and the objects are at, in vertical equilibrium. So n equal to mg, which is 5g, 15 newtons. So yeah, here let's say for f equal to 10 into acceleration of 10 kg block, and 1 equal to mg plus m, which is 10g plus 50, 150 newtons. Yeah, there are many cases now. First case, let's say the the net force in the x direction is not uh, more than 0, and we know the friction force can be up to a maximum value of mu into n, 0.2 into 50, that is 10 newtons. So if the driving force is 20 newtons, but what if the driving force is 6 newtons? What if the driving force is 6 newtons? It doesn't move. So friction becomes what? Let's say there is some friction. Yeah, 6. Doesn't. So if you apply a 6 Newton force, the static friction gets adjusted to 6 newtons. So that force doesn't allow any relative motion between these two surfaces. But there is a chance that these two objects can move as a whole, and there is a force of 6 newtons, and there is no friction here. So obviously this will be 6 by directly. This can be directly calculated using 6 by 10 plus 5. So this will be the acceleration of the system, and the friction force will be what will be this? There will be some friction here, there will be friction here. That could be calculated using these accelerations again. So yeah, that's cool. But what if?
Sushanth, you can leave whenever you want.
Okay. Okay, let's get back to the question. Okay. And now the friction can be a maximum of 10 newtons. So let's set the acceleration equation again. 5 into a5 equal to 20 minus f max, which is 20 minus 10. 5 into a5 equal to a5 equal to 10 by 5, which is 2 meter per second square. Okay. And let's try to calculate the acceleration of 10 kg block. Acceleration of 10 kg block is f by 10, and we decided the f value to be 10 here. So 1 meter per second square. Yeah, this can happen. And never try to acceleration of time is 1 meter per second square. And this one. Never blindly believe the answer you get. Just once check back what happened. There is some combination of blocks, and we tried to pull this. It came out with an acceleration of 2 meter per second square and 1 meter per second square. So yeah, this could happen. There will be some answers in cases where you try to pull this, and this comes out as 1 meter per second square, and apply force on this, and this will be 2 meter per second square. This is vague, right? You try to pull the upper block, but the second one is coming faster than the first block. These are vague answers. So after you get an answer, please try to check back whether it is correct or not. This pretty much sums up what a block on block is. And okay, that's all for today. Yeah, thank you.